This Saturday is 29. No, it's this Saturday. Sorry, first.
31.
Sorry.
31.
31. Okay. 11 a.m. here. We'll have a visitor from actually it's a Canadian company. They are working with neodymium magnets to create big magnets for different applications. They need supply from neodymium, which is mainly from China, and they are very dependent on that, so they are looking for different sources of neodymium. For example, extracting neodymium from fly ash, which is a residual from thermoelectric plants. After you have a coal plant, you generate thermal energy, you generate a lot of black carbon with some fly ash. Eventually, flue dust from smelters. Sorry, most of you are focused on. One of you are focused on germanium. Isidore, I think, is focused in zinc. I don't know why, because zinc is a different thing. We have different sources of zinc. The rest of you also focus on germanium because the assignment was on germanium, isn't it? Okay, good. I didn't go to neodymium. So this guy is coming because he's offering a thesis to work in leaching of any of these. We don't know which one. In order to extract neodymium, we're not producing magnets, but so we want to produce neodymium oxide or whatever thing is easy to manage. As you may know, producing, for example, a pure metal with electrowinning sometimes is more difficult. If you want to produce, for example, lithium, metallic lithium, it's going to be really, really tough because it's too reactive. Any alkaline metal, for example, is very reactive. It's better to have it in a stable form. So that will be on Saturday for only Erasmus students because this is for a thesis proposal. So they will, the main idea, no. Well, unless you want to do a thesis because he's offering, if we do some work here, in leaching, then you can spend 1 to 2 weeks in Canada and be connected to the company. That he will offer a thesis. Understand? Another news, we have a meeting with Mezzo, Alejandro and Natalie. So they're going to ask for another 2 students for a thesis. So you're going to be trained on that because the one that they had last period was Enebel and Javier. We were here, so they learned kinetic, flotation, so they're familiar with that, bubble size, all this stuff. So I'll be more focused on that for those who wants to work in flotation. It will be concorsel or final course particular. He's interested, so he's the first candidate. You're interested? Okay. No, you talked to me before. Okay. Yeah. No, I'm telling the group that he manifested interest, so you will be trained different activities, measuring bubble size and stuff like that. Okay. That's it. News. Conference is really, really bad. Just
the guys from Metsu is doing the same.
Sorry.
The guys from Metsu is doing the same.
No. I'm telling you that I had a meeting 1 2 weeks ago. So they wanted to have 2 new theses. By the way, Enebel and Javier are working in Metsu now. One is working with Rodrigo Grau. Enebel is working with Rodrigo Grau, which is a former chemical engineer from here. He's the CEO of Flotation R&D. And Javier is working with Alejandro Yay, also Chilean guy, at the university, in a more concorsel, but for more technical sailings. He speaks Spanish, so he'll be marketing Peru. So good news. 80-70% of students already have a job. That's very good. Okay. Understood? Okay, now coming back to the design course. This is conference was horrible. I can show you some of the presentation. Really bad. Keynote speaker, Canada, really bad. I was complaining with the organizers, so we can do a better job. Next conference on recycling will be in Rome next year. So I'm trying to invite third cohort of Erasmus, because we are in Austria, going to Rome for the conference. So I asked them for a special flight for students. Okay? It's not a big deal, the conference. It's not really good. Not bad. Coming back to this sustainable engineering, because you have pending the presentation, but before going to presentation, some piece of advice, not going into too much detail, technical of design, scaling up, stuff like that, but whatever thing you do, you need to have a mass balance. Let's say you have given amount of construction, million of tons, whatever estimation of, if you don't have a number, for example, you can say it will produce this amount of copper per year. We can estimate the amount of fly ash. We need to have an estimate, million of tons, the raw material accumulated and produced. Remember, we don't need only a specific point in time. Always, you're here and projection. For example, if we talk about tailings, in tailings we have abandoned tailings, disposed, active tailings, the running disposing material, and future construction. Okay. It's important when you do a mass balance, the total amount must consider year and projection. We are not in a static point. Understand? And then you have some paper, some information. You have one paper says 10 ppm of germanium, another one 50, whatever number, germanium. Nothing wrong with uncertainty. We're looking for that. And then from there you can estimate what is the availability in time of the material. How much do we have? Okay. This is the raw material. And then everything is internet. I mean, we're not looking. Remember, the first phase of a project is 50-60% uncertainty. We showed that. Okay, 50-60% uncertainty. And then market. When you say market, this is extremely difficult. Actually, you need to pay for more detailed study market. But usually, we use as a reference U.S. Geological Service, a starting point. When you have price, you have the larger producers, you have a number there. And again, in market, it's demand, time, demand. Very important to understand if the demand is based on the element kilograms of neodymium pure, or it is on germanium oxide. You know what I'm trying to say? It's not the same 1,000 tons per year of lithium carbonate or 1,000 tons of lithium carbonate based on lithium element. Understand? So sometimes study markets, even this assessment is wrong because it's based on the mass of the molecule, not in the element. You understand what I'm trying to say? So to avoid any confusion, always work on the base element. Germanium, lithium, the element. Do the calculation to correct with the molecular weight. Okay. Mass based on element. You need to correct some of the time. It says lithium carbonate tons based on lithium elemental lithium. Okay. And to do that, you need to have the molecular weight. So, for example, you can have different type of crystals. You can have I want to just made up some names. You can have germanium chloride, germanium oxide, germanium sulfate. You have different sources of data with different numbers. You cannot compare both. You know what I'm trying to say? In order to avoid this confusion, you correct this number in the germanium equivalent tones or whatever element. Understood? Same with the price. Same thing with the price. You will see a price that says the 400 US per lithium carbonate per ton of lithium carbonate. You need to correct for the equivalent lithium in order to compare different possible elements. Okay. It's just to clearly know the molecular weight, which is not that difficult, but it's extremely difficult to get this data. We are not doing an engineering study, we're just learning. Okay, so you want to have more accurate meaning close to reality, accurate data. You pay for a report. A report, it costs 2,000–3,000 US to have the study market report. Okay, you pay for it. Okay, but this is just to understand how it works. Got that? That will be how much can you get, how much is willing the market to receive. Why is I'm doing that? For example, we're saying we want to be sustainable, we want to use all the material, blah, blah, blah. So we are sustainable because in all mining school, they have a pilot plant that doesn't generate any kaolin. It generates a geopolymer, which is used to build roads. It sounds great, isn't it? We have millions of tons of tailings. It can be used for construction material, which is great. But Escondida produces 50 million tons per year. Only Escondida, 50 million tons per year. So the total amount of material, it can be used to, let's say, to put roads in the entire country. You know what I mean? So it's too much. It's stupid. Okay, so how much can you get? It's available. How much is the money? You need to have both. Understand that? Always the mass balance. Another funny story, especially in innovation, there's one guy, a company that they're producing frothers for flotation, frothers. They are called environmentally friendly frothers made from wood, from vegetables, from plants. Okay, so the question, do you know how much is used in a plant? You use very little, you use 10 ppm, 5 grams per ton, 10 grams per ton. It's not a big amount, but if you are producing 150, if you are processing 150,000 tons per day, you need 20 cubic meters per day. It's a lot, okay, one plant. So to make the story short, we asked, how much can you get from a tree? It was 1 gram, 2 grams. So in order to produce the frother required for 50%, maybe not the number, I don't remember, 50% of the mining companies, you need to have half of Argentina with trees. The half of Argentina with trees only to get the frother. Okay, do you understand where I'm going? So always the mass balance, always. Simple calculation. If you have 100% error, it doesn't matter. But it's not 1,000, it's not a million. It's an order of magnitude. It's a very common mistake, very common mistake. And what happened? We laughed. We laughed. Not to mention that having frothers, frother is not a good idea having a very complex process, because frothers are bottom products, meaning they are secondary products from refineries, so they are discarded products. They are very cheap. They mix, so the quality of a frother is not good. When you say Dow Frog 250 or F150, it means you have the average molecular weight. If you make an analysis of that, it will change in quality. So it's a not good quality product, very cheap, so no good effort having a renewable, or sorry, a degradable or environmentally friendly product. Understand? So it failed for two scenarios: mass balance and the alternative products. Okay. This is a simple part. Now scaling up. I saw in most of the presentation you start with neither a batch test, and then you end up with a plan and capex opex, but you don't have the size of the equipment. So how come you have the price of the equipment? You don't even know the kinetics. How? You're not magicians. You cannot have it, you know? To make it simple.
What in the case of the
Sorry, Hernan, are you hearing me? Can you see the thing that I'm writing, understand?
Yes, I'm here.
Now I want to talk about a little bit of kinetic. Go ahead.
you have mentioned about the market and the price.
Yes.
So how we can calculate the market and the price?
US Geological Service, you have all the data. You have a lot of data. Also, there are two important books. It's not sure about how to write it properly. Ullman's Industrial Chemicals is a very 30 chapters. Ullman's. I'm not sure how to write it. Ullman's, and we can have it. PDF. Kirk or Mer. I'm not sure about the spelling. These books, they show process, study market, possible products. This is about 10,000 pages. I'm not kidding. 10,000 pages. Those are the base ones. Simple to get. I'll get for you. Tell me to get the number. And also Internet US Geological Service. Some of you already quote that. Some of you already quoted the Geological Service. And the good thing, you have different report. For example, Neodimi. You have a report 2023, 2022, 2020. Understand? It's not that accurate, but it gives you a reference.
What numbers?
Sorry?
What numbers?
What number? What are you talking about?
You say I have to search the numbers.
No. The right names.
Ah.
The right name. I have the PDF versions. No, you can send it to the group.
Okay.
Or, you know, both of them. Those are, they have the processes, the flow sheet, okay? And also what product do you have in markets? So study markets. Even you have some geological characteristic for rare earth elements. It will show you. It's very interesting. It's a big book. They have different versions, and I think it's a good starting point when you have nothing. It's better than just Google. Okay, it's very precise. Okay, now I want to tell you if you are either. There will be a short scaling up here. If you are either leaching, if you are doing flotation, if you are doing a chemical reaction or crystallization, whatever thing you do, leaching, flotation, crystallization, you're producing something. Crystallization, chemical RX, chemical reaction, whatever thing you do, you usually start with a batch test. An experiment can be this size, 1 liter, whatever scale. The scale is determined by the detection limit. If you're working in part per billion, you cannot work in a tiny reactor, because if you have one drop, you will not have enough material to be analyzed. So the size of the sample is determined by the analytical technique that you have. If you're using atomic absorption, you need 10 milliliters. If you're using ICP mass, it depends on the detection limit. Before designing any experimental test, you need to know what are the analytical capabilities that you have, okay? And you end up, usually all the process, regardless the process of reaction, most of them are first order in terms of reaction. When we talk about the velocity of the reaction or the extraction or whatever thing, First order means you have, this is the element that you have, either disappearance or recovery. For use the same. You can work on how fast it's being removed, disappearing, and how much do you recover. 1 minus how much is disappearing, how much are you recovering. You understand that? You will be conducting an experiment with methylene blue, injecting ozone with air for the mass transfer. And you will change the bubble size. You will see how the methylene blue is being oxidized by ozone and is changing in color in time. Okay, and that is function of the interfacial area. Okay? So you see how it's being removed. If you have a flotation, you have particles, and you see how many particles are being removed in time, and you say how many particles I have remaining in the tank. See, if this is the case, you will see something like that. They are decreasing in time. Same process, and you say, I wanna see how much are getting out of the reactor, counting, relative to the original mass, and then I use will be the recovery. You got that? So either way, you can get the number. Understand this part? That we call it kinetic test. And when we have a first order, it means yes, you will see using that. Benjamin is setting up the experiment for us. He's the TA. Benjamin. It can be anytime. You can repeat it, measure bubble size, and all this stuff. Okay. We have a new ozonector. Last semester it was broken. And when we have this minus kx, we are saying that the velocity in this case of disappearance, that is the negative one, okay? The disappearance, it's proportional to the concentration. Understand? Proportional to the concentration. So it will be differential, okay? Again, what I'm telling you here is valid for leaching, flotation, sedimentation, whatever process when you're changing a property. In this case, it's concentration. If you remember some calculus, you will end up with Ex, K, T. You make the integration of that, you will end up with the logarithm. Okay, remember that? If you don't, let's do it. You end up with the logarithm. And then when you solve from 0 to time to certain time, you end up with, it can be the concentration or it can be the recovery. The concentration in time will be concentration 0 exponential k times t, because it's the logarithm. You end up with this concentration, and then you express it in terms of recovery in time. You will end up with maximum recovery, because you have a maximum amount that you can recover in time. You have 0 to 100 here. You have something like that. It's not the same leaching particle this size for 1 year, because you have inside the particle, as you say last class, occluded. So you will extract 40% maximum. Yes, you say occluded. Okay, and if I take the same material and I use a very, very fine grinding, I use 1 micron particles. When the grain size is 10 times, grain size is 10 times the particle size, the ratio, you will have 100% extraction. So that is liberation. Remember the liberation concept that you have in all? Okay. So this maximum will depend, in the case of leaching, in the case of flotation, on liberation. How much material you have exposed on the surface in order to be removed. Understand that? This is a large particle, small particle. Okay? Large particle and small particle. So this is the parameter for the maximum, the plateau. You don't even need to do an optimization. You will see the plateau. You have the number here. The plateau will be the maximum. Okay? And then you will have K. This is a very simple model for first order. We're saying we have one single K. This is important because in process design we will change that. With single K means all the particles, all the bubbles, all the elements are exactly the same. Same size, same geometry, same liberation, same absorption of reactor on surface. Have a single characteristic. Understand? We will change that again. This is a very simple model. Just understand the scaling up. This is for a batch test. It's not for continuous test. This is a batch test. The other trick, do you remember the trick, Isidora?
The what?
The trick
Trick?
to get K value?
Oh.
Master Acuna trick.
What trick?
You must remember Can you see Hernan?
I see very well.
Okay, good. Actually, you know what? I'm gonna here. Okay, let's say we have here 50. We have 60. 70. Okay, I want to assume that you have 100. So I want to assume that you have 100. Okay, listen up here. What happened when time here, the time when the reaction is going, is exactly the same to 1 over K. It's exactly the same to 1 over K. That will be 1. Just for the okay. So when time is equal to 1 over K, means that this value is 0.632. Calculate. Do exponential of minus 1. 1 minus 2. Calculate. See. Now you remember? Leaching. Leaching course. You pass very well. What is the value? So the magic number for you from now on will be 63.2%. This is for whatever dynamic system, whatever kinetic, whatever thing you have when you have first order. This is also, listen up, this is also when you are doing process control with Professor Berg, dynamic system, you end up with the same thing. A dynamic response of a level temperature, you end up with a dynamic first order. It's very important what I'm telling here, because this is valid for chemical reactor, leaching, flotation, process control, dynamics, settling. So pay attention here. Okay? Did you have the number? What is the number? In calculator, you need to have 1 minus exponential of minus 1. Al cálculo, Hernán. Calculate.
Calculated.
What is the number?
0.63212.
Perfect. Okay? What does it mean? When I want to model experimental data, I need to look the plateau first. The plateau will be this maximum value. Agree? Easy. And now, since I know this fact, I'm going to say, when I reach 63.2% of the response, this value, in this case, because I put 100%, but in some cases it's going to be different. You have 80% recovery, it will be 54. You understand? So it depends on the maximum. Remember, always depends on the maximum. In this case, it will be 60.2. In this case here, look, you will say here K is 1/3, in this case, minutes. So this, it will be your first guess of the parameters. Then you can put either solver, MATLAB to optimize, but whatever fitting process that you do, you need to start with a guessing parameter. This is very good. So you just in 10 seconds can you determine the parameter for first order kinetic test. Understood? So you just see in dynamic response, even when you are doing process control, you have a small step change in a valve, you see how it responds, you will see it in process control lab, you will see the response, then the number, delta time, and you can have, in this case, a little bit different because the model is not K times T, it will be T divided by tau. So in this case, it's the same, it's T is equal to tau. And we call it the time, we call it time response constant. And usually you will see some sensors or instrument, you will see something like P63.2. You will see something like that. This is the characteristic time response of a sensor. For example, if you have an ozone sensor, in liquid phase is very slow. It will be 20, 30 seconds. That will affect strongly your process control. But let's talk about that in October, when we are doing process control. Understand? This is very important to understand. It's the basis for kinetic, understanding the concept, understanding that can be used in many fields. Of course, you go to solver, you have this model, but you already guess the first parameters, and then you optimize, you minimize the residuals value. The residual value will be the experimental value minus the model. And then you analyze the residuals, and then you get the confidence interval depending on the number of points you have. If you have less than 30 points, you need to use the student. If you don't, you can use the plus minus 2 sigma. If you're using a 95% confidence interval, you determine if you're using 80%, 90%, 95%. Okay, but this is the chapter of statistics and with Professor Perry. So please review that. Okay, we will come back to that in the process design course, a little bit more complex because we're using K with distributed value. But for this process, for this sustainable engineering, this is enough because we want to understand how to scale up. Okay, got that? We haven't finished.
The maximum recovery dependent on the single K.
Come again, say it again.
The maximum recovery that we gain here is dependent on the single K that we got.
No, they are independent. No,
So
independent.
you are considering the
No, completely independent. This value, in the case of rotation, will be depends on liberation. Let me clarify with an example here. The size will affect both K and maximum recovery, always. Let me show in a leaching example. That will be log scale in order to understand log of time. Okay? if you have 1 meter particle, damp leaching, 1 meter particle, you will end up here with 30% extraction in about 3 years. 3 years. This is the kinetic, very slow. If you go, that will be 1 meter, diameter will be 1 meter. If you go to a heap leaching, when you either agglomerate the particles and you end up with, it will be something like that. Remember, this is a log scale. You will end up with 60% recovery. Well, to be fair, 65%, 70%. That will be the time will be 3 months. Okay, for 36, 10% of the time. Sorry? I didn't get it.
Particle diameter.
Yeah, there would be typically 3/4 inch, 2.54 is 1 inch. Oh, this says 3/4 inch, small. Okay, less than 1 inch. So, from 1 meter going down to 1, we increase the recovery 30%, and we reduce the time from 1 hour, from 3 years to 3 months. Now, if we go to a regular agitated tank leaching like a gold or autoclave leaching, autoclave is different. We need to put temperature in order to leach, but let's say in fine particle, we will end up 80, 90% when you have mesh, I think it's mesh scores, mesh 65, I'm not sure, that should be about 300 microns, which is the case for gold, 300 microns. It's like sand. You touch it, you feel it's like sand. That will be easily 3 hours or 1 to 3 hours. Again, 3 years, 3 months, 3 hours. Why don't we do everything this size? Because cost. Reducing size, it has cost. Understand? Okay. More extreme. Actually, we did that with one colleague. We have refractory minerals with gold. And those are in the study cases, by the way. And we end up with that will be 20 microns, more liberation. Well, that is, let's say, 30 minutes. I just made it, I don't believe in that. I made it up the number, but we did an experiment with refractory minerals. It means arsenopyrite gold minerals. If we do it just like this, it will not work because it will generate an ash of sulfur. It will not work. So we liberate it, okay? But it's absolutely impractical having 20 microns for leaching because of mixing. Technically, what is the parameter that will influencing this? It's apparent viscosity, but we are interested in the shear stress. Shear stress. It will be like a paste. You got that? Okay, now I understood. Again, actually from this plot you can determine K. And then you can have a plot size and K. Sorry. You can have a plot K size and also maximum recovery, or maximum in this case will be extraction because it's not flotation. Size. So the answer is yes. Size affect both kinetic and maximum extraction or recovery. In the case of leaching and flotation, that will be given because of the liberation. Got that? In the case of mass transfer process, it will be for the interfacial area that we have. You have a pure crystal, this size, a pure crystal, salt, pure crystal, salt. and then you dissolve it, it's gonna take a long time. But if you have the same crystal, it's pure crystal, not 100% liberated, you will end up with 100% recovery. It's not the case like this, you understand? 100% recovery. But it will take, let's say, 2 weeks, just to put a number. If I take the same crystal, crush it, grind it to 1 micron, it will take 10 minutes and 100% recovery. So in this case, the size influences the interfacial area. We want to add another experiment because it's very simple, you know that? The dissolving coarse and fine salt. Remember we did it once? We have TAs to do that because it's good to them to see the curve of the experiment. It's an experiment when we measure the dissolution of salt, sodium chloride, coarse particles. You have a specific curve. It will not fit an exponential curve because you have a particle that is decreasing in size. So it's changing the interfacial area. But if you have only fine particle, it will fit very nice only exponential. I prefer them because they have time and they need to have more experimental data. Remember, I think it's a very nice, simple experiment. We usually do it, but now we only process the data to see the difference in the curve. Same material, same liberation, but the size influences the behavior of dissolution. Understand? But I want you to see it. You can set up. You haven't been my TA in mass transfer, no, never. But you did this experiment.
Yes.
Yeah. Now we just fit the data. Yes. Okay, very good. It's taking too long, but I think it's very important to understand that. Okay. We're not scaling up yet. And now, you have an experiment, let's say, in a size of half a liter, batch, meaning you put all the thing in the soup and process and extract material. This is batch. Okay? And then you can either scale up to a larger, again, batch, industrial, depends on the amount that you want to process. If you have a large amount, you need to go to a continuous reactor. And please remember, all the time put baffles. Otherwise you cannot mix. You will generate a vortex. Baffles, that will be the continuous reactor. Let's put a pump. Look, I'm putting here something that we call, please do it all the time. I review many engineering projects with good company. They don't have the draft tube, they put here and it doesn't mix. You need to have a draft tube in order to, put it here. Very important, this impeller, baffles again, and then you have here the product. This is a continuous reactor. We call it, how do we call it, Crystal? We have a continuous reactor. Very well. CSTR stand for? No. Completely stirred tank reactor. Completely stirred tank reactor. Complete mix. How is that? Because when we put, let's say, a colorant, blue methylene or whatever colorant we put here, we go to the reactor and instantaneously everything is red. And then the colorant is decreasing in time. This is residence time distribution. We will see that in process design. Okay? So we have the two cases. In this case, always, the very important parameter, and you see most of the mistakes, is not the RPM. It's the Reynolds mixing number. We're not seeing it there, but in this class, I'm only interested in having the same tip speed, which is RPM or second times diameter. You need to have this tip speed exactly the same in your batch reactor. Not RPM. RPM is wrong. Completely wrong. It's not the same. Understand? It's the velocity that you have here. It's the rotational frequency times the diameter. Okay? You get the tip speed. Tip speed is the right number. Okay? Why is that important? Because the power consumption that you have in any reactor, the power consumption for mixing, it's proportional to diameter to the fifth. To the fifth. You cannot make a mistake there. The energy is really, really big. I mean, going from this size to this size, the power consumption increased to the power of 5. It's a lot. Understand that? Okay, too much process design, because you have a course of process design. Let's go directly to the scaling up. So when you have a CST reactor, let's say the extraction in time for a CSTR, it will be again maximum extraction that you have on the lab. But in this case, it will be K, the value that you get from the lab, times tau, which is the residence time, divided by 1 minus K tau. Okay? So the modeling is different from a continuous reactor because the mixing is not the same as a batch test. Understand? Careful here. When we talk about tau, we need to have the volume effective, which is volume nominal, the size of the reactor, volume square cubic meter, times 1 minus mechanical parts. These mechanical parts can go from 0.1 to 0.03 because you have things inside the reactor that is using volume. You need to have only the effective volume all the time. And now tau will be effective volume divided by Q, which is volumetric flow rate of the pulp. Remember, it's the pulp. You need to calculate. You're good on that. Pulp. Pulp. Volumetric. Cubic meter of pulp. Yeah, to remember your mineral processing courses. Let's say you have the TPH, which is usually solids only, divided by P sol, percentage solid, 100, okay, divided by raw pulp. Remember that? Raw pulp. It will give you the cubic meter per hour in this case. Okay. You need to have, this is only the solid, we will give you the tonnage of pulp divided by density of the pulp, we will give you the volumetric volume. Remember that. Don't you or do? No problem with me, Professor Bert, you need to be prepared, but not with me. You don't remember saying it, you remember that? You're talking about a pulp, we have solid particles with solution. Okay, this is how many tons per hour are you putting in the plant? Solids for mineral processing. If you divide by the fractions, just
Dry solids.
sorry? Dry solid, usually, always. When you have TPA, it will be dry solids always. Okay, it will be solids, the tonnage, always. Then you divide by the fraction of solids, this percentage of solids by the 100, it will give you the pulp as a mass, tons per hour of pulp, that is water plus solids. Okay? And then if you multiply, you divide by the density of the pulp, which is ton per cubic meter, it will end up with volumetric. In this case, will be cubic meters per hour if this is tons per cubic meter. Okay. Pulp density. How do you determine the pulp density? In order to determine the pulp density, you can either work with the solid content as a fraction or percentage. To avoid confusion, we work with solid percentage. It will be P solid. Yeah, I want to do it like that. This is percentage. This is P solid percentage divided by density of the solid particle. 2.6 if it's 2.6 if it's quartz, mineralized 2.9. If you have lead, it's going to be 4. You see? Okay. Plus 100 minus P sol, because it's in percentage, everything. If it's fraction, it will be 1 minus the fraction, divided by density of the solution. If you're using saline water, you need to have the density of the solution. Okay? That will be a completely tank reactor. We never use a single tank. Never. In flotation, do you have a single flotation cell? You have 4, 6, 8, some cases 12. See? In leaching, how many leaching reactors do we have? So again, for continuous reactor, we never have a single unit. Okay. I want to finish with that because it's taking too long. But again, I think it's important to clarify that. If you compare, and again, this is valid for flotation, leaching, chemical reactor, and everything when you have a first order process. If you have here extraction, and then you have, that will be batch first order. If you batch first order, it will be E max 1 minus exponential K, minus K time, okay, with this curve. But if you have CSTR, it will be, all of them reach that, okay? That will be 1, that will be continuous, 1 CSTR. You can make the comparison. You can make a plot already. Just give a number. You can make a plot. You compare here K time 1 minus K time times E max. Give the same E max 100 and compare with the same K. See the plot. Make a plot. In order to understand, in order to be a very specialized, in order to be an expert, you need to do it. Make a spreadsheet, put the number. Usually we use we don't use 1, 2, 3, 4, 5. We don't use an arithmetic progression. We use a geometric progression. Okay, that would be something like 2, 4, 8. Usually we use square root of 2, which is 1.4. We use a geometric progression because here you need a lot of very close points, and then you need to very separate. You don't need to have 100 numbers. With 12 numbers you are done. You understand? Anyway, you get time, and then you give a batch and CSTR. So you will see the difference. With the same K, you use the same K. Same time for both of them, same K, different model. See what happens. Okay? So this is not that good, but if I put two tanks in series, it's gonna be better. These are 2 tanks in series, a bit better. If I have 6 tanks in series, CSTR. And if I have infinite number of tanks, I will reach batch test. That's the reason, because in design, we have 6 flotation cells, 8 flotation cells. The current circuit for Escondida will be 6. In the past, we used 12. This is too much. Then we are not cleaning, we are producing a concentrate with less concentration than the feed, the agar criteria. Okay? But that's the technical reason. So for leaching, the experience says you need between 4 to 6 cells. Then if you see an autoclave reactor, you will see 4 vessels. Because of that. Because this is an economical, it is an economical evaluation. Imagine that. Let's say that you want to recover this amount. It would be your design extraction. For a single tank, you need this time. If you need this time, you will need for the same volumetric material processes, cubic meter per hour, you will need a huge tank. Okay, you're determining the volume here of the reactor. That will be tau. Remember, you have tau, or let's say volume, it will be volumetric flow rate times tau. So the larger the number, the larger the size of the vessel that you have here. Understand? And here you have 6 tanks. You have a lot less time. This is the total time. This is total time. Time total 6 tanks. And then to calculate the volume of each specific tank, if you sum all of them, always you want to have less volume. Okay? Again, if you have a single tank, it will be very big. If you have 6 tanks, 4 tanks, 2 tanks, the total volume of the reactor is going to be smaller than a single one. And then it means cheaper. Can I have 20 tanks? Yes, but 20 tanks means agitator, more part, more mechanical part. Then you are limiting you have more cost in maintenance, cost in materials. So for leasing, the engineering practice is 4-6. But of course, you need to analyze case to case. Okay? But this curve now for N-tanks in series, how it looks like the extraction curve, the flotation curve. That will be 1 minus. Sorry, it's always I'm gonna do it like that. E max, always is E max, always. It's a limit, a plateau. It will be 1. That will be K. This is a tau divided by N. This tau is the total tau, total. And to the N. Now you can compare the plots. And when you have, let's say, 12 tanks, it will be really, really equivalent to a batch reactor. Okay? Understood? What are doing our colleagues from metallurgy, mineral processing? What are they doing? Because they are ignorant. They don't understand this single equation. They don't understand. By the way, tomorrow I have a presentation in the FLOTAC conference. I'll be talking about this. What they do, I can show you. First Smith say, we are that ignorant, we don't know anything about mixing anything. Okay, we have our batch test, we want to get this recovery, let's do it like that. And in order to see how much time do we need in a continuous cell, we apply a factor of 2.5. You know what I mean? This time here times 2.5, it will be the time for a continuous reactor. Why? Because in practice you will see recovery, great recovery in batch is really, really far from a plant result. This is because the mixing is completely different. You know the equation, they are using the wrong equation. You cannot use the exponential because it's a completely different equipment. You will see that in the resident time distribution. We know this very well, the mixing, because we invented here, believe it or not, resident time distribution with radioactive gas. Here, Professor Janat, 30 years ago, working for many years. Okay? You know that. So you will know that. Perhaps you already lectured on that. This is an ignorant factor because, but we know it's more complex than this. Also affect the froth capacity in the case of flotation. In the case of flotation, when you have a batch test, you're removing my hand, so we have 100% recovery. But in a big cell, it's not the same. Restriction for, okay, but this is a different story. Okay, important for this lecture here. Anytime you want to scale up from a batch test in order to know the size, you need to have, you already know, 4-6 tanks for leaching. You know the equation. You can have experimental data. That this is influenced by the size. You already know that. Size influence K. Okay. Remember, Emax size, it will be something like this, related with liberation. K is a little bit tricky if you are desperate and you have an experiment, let's say in 10 micron, and you want to see what happened in 100 microns. My recommendation will be K size 1 over K size 2, it will be size 2 over size 1. Something like that. Because the interfacial area at the end, it will be volumetric fraction divided by diameter. So if you reduce the diameter, your kinetic will increase proportional, 1 over the diameter. If you are desperate and you don't have a number, this is a good thing. You cannot use a kinetic value in an experiment of 10 microns if you're using 300 microns. You know, you're going to be a lot slow, and we know that. If you have that data with different sizes and kinetic, okay, use this data. But not, you can use this number, you can estimate it, okay? So this is not that difficult. Again, batch data, knowing the amount that you want to process, how many tons per hour, which is determined by the market. You decide if that will be, it's going to process 2,000 tons per day, to say a number. And then it will work with 30-40% solids, 10, it's expensive, 20% is the limit. These particles, you know, and then you determine the volume. Do the calculation by hand in order to see the size of the equipment. The last thing, before I forget. And then if you have huge amount of tonnage, and you end up with 200 cubic meter tanks, too big. Then you need to say, okay, you end up with, you know, let's say 6 tanks. They are really, really big. with the calculation. It's not possible to handle. Then you divide the stream in parallel lines. That's the reason, because in a circuit you have parallel lines. You know what I mean? If you have a circuit of 630 cubic flotation cell, you need 2 lines. But if you have 300 cubic cells, 6 cells per row, the number of cells per row is determined by the kinetic that you want to achieve. But the total amount, the number of rows, is determined, the actual site, 300 or 600, is depending on the amount of material that you are processing. If you have too much material, you need to divide it in 3, 4, 5, 6, 10 lines. You understand? Is that different? The largest flotation machine that we have today is 630 cubic meters. In the case of leaching, 1,000 cubic meter reactor is reasonable large. Okay? Got it? But you will see. I'm sorry, but you need to do the calculation, see what happened with the number. Is the only way to understand and to learn. The only way. Okay, you have a question?
So the n comes in series.
Yes.
If the n, assuming that the n is 1, it means that
you don't use this equation.
If you start, I'm saying.
If you use n1, you don't use this equation. You need to use this equation.
It will look like
yes. Okay. It's a little bit more complex than this, because in order to get that, we use residence time distribution, and if you see the curve, it will fit beautifully. Experimental data. But this is for process design course. Okay? We'll stop here. Okay, Hernán. Espero que haya entendido. Did you get that? Tenía que hacerlo porque estaban calculando wrongly. They end up with CAPEX, OPEX. We don't even know the size of the equipment.
Anote todo.
Okay, perfect. So, see you. Please be aware of the email because I'm changing schedule. I'm really busy today. See you.
Okay.
See you, Eduardo.
See you, bye. See you, bye.
Okay. Here's the guy. Okay.